This is the 28th lecture of this course. Recall that in the last lecture I said we intend to prove that well, let me write as I start, let V be an n dimensional vector space over F, n dimensional vector space over F, and let us say let W be a subspace having proper subspace of V. Then we will prove that W is the intersection of well, let us put it in this way. So, let us say W equal to D, which is n minus 1, then we will show that there are n minus D hyperplanes whose intersection is W. So, for that we will prove that. So, for that let us recall that given a set, given of course non-empty, given a set of vectors, non-empty set of vectors in V, we have the annihilator of that set S defined as for all S in S. Okay. So, therefore, so if even if S is not a subspace, still S upper naught is a subspace of, so this is a subspace, but this is a subspace of V star. Okay. Now, in particular assume that we are dealing with a subspace W, then let us ask with W naught. So, W naught is the annihilator of W. This is precisely the collection of all linear functionals which vanish identically at W. Okay. Now, let us observe one very simple thing, that if F is a linear map from V to F, is a linear functional from V to F, such that F vanishes on every point of W, then we can indeed talk about the following map F bar. So, this is the projection map that sends each every V to V plus W. And how is F bar defined? So, remember, I mean F bar, I mean if, well, let me first write, then it will be more clear to you. F bar V plus W, we define it by F V. First of all, we need to make sure that this is well defined. That is very easy to see. If V plus W is V dash plus W, that is V plus V dash lies in W, then what happens? Then V plus V minus V dash lies in W, but F vanishes at every point of W. Okay, F vanishes at every point of W. So, therefore, F of V minus V dash is going to be 0. So, F V equal to F V dash. So, this shows that it is indeed well defined, and it is easy to show the way it is defined from the linearity of F. It will follow that this F bar is linear. So, therefore, from an F we get an F bar, and the way it is defined, that shows the following: F bar compose, F bar is a linear map such that F bar compose F, phi is F. Well, the remark which I want to make here is, earlier while dealing with first isomorphism theorem, we see that we only at that point of time we were considering quotients only by the kernel, but here W may not be the kernel of F, it is rather a it may be a further some subspace of kernel of F, right. But even then I mean if you remember how we proved the first isomorphism theorem, if we adopt the same strategy, even for subspaces contained in the kernel, the same goes through, and we get a map analogous to what we have seen earlier, and we get a linear map such that this happens. Okay. So, in general this map is not injective, that is very easy to see that in general this map is not injective. Why? So, in order to, since this is what we have proved to be linear, so injectivity means we have to show the kernel is trivial. So, kernel of F bar V plus W is F V, So, if this goes to 0, then that forces V to be inside the kernel of F. Okay. So, if you take a vector V from the kernel, but outside W, because W is a subspace of the kernel, then you see F bar V plus W goes to 0, which is a non-zero vector which goes to 0. Therefore, this map cannot be injective. This is injective if and only if W equal to kernel of V, W equal to kernel of F. Okay. Anyway, that is not the main point. So, as I said, if we adopt the same strategy, we get a linear map such that it happens, but this map will not be injective. But earlier, and if we take W to be the kernel, then it will be injective, which we have already seen. Anyway, let us come back to this situation. So, what we have is the following, that in one hand we have W star, what is W star? No, this is W naught. In one hand we have W naught. So, on the other hand we have V quotient W star. So, this is the dual of V quotient W. What we have done is, starting with F, we have sent it to the corresponding F bar, try to see that F bar is linear. So, this makes sense. Okay. Now, the next step is also very obvious. This map is indeed linear because F plus G. So, F goes to F bar, G goes to G bar. Okay. So, this we have done for any F. So, therefore, F plus G bar of V plus W is defined as F plus G of V. This is for anything, right, for any F lying in W. So, if F and G are in W naught, W upon naught, then F plus G will be W upon naught, and we do this general, we defined, so from this general definition we see F plus G V plus W is this. Now, F V plus G V, F V is as usual F bar V plus W, similarly this, and for the case for scalar multiplication is also trivial. So, this is a linear map. Okay. Now, okay, fine. So, this is a linear map from here to here, and what about the injectivity or surjectivity of this map? So, the surjectivity is obvious. So, suppose I have G in here. So, that means from V mod W to F I have the linear map G, and from G to V to V mod W you have the projection map pi. Okay. So, what about G compose pi? So, this is linear, this is linear. So, G compose pi will be a linear map, to be linear functional on V, linear functional on, as a linear functional on V. We have to make sure two things. Well, we have to make sure two things, no, not two things. We have to make sure that G compose phi, that, we have to two things. I will do one step by step. So, in the first step we have to prove that. So, this is in V star, we need to check this lies in W naught, this is one thing, and the second thing that I need to check. So, these are we need to check G compose pi bar is G. Okay. So, these verifications are trivial. For example, if you take any vector from W here, so W comes to 0 in V mod W. If you take a small w in from capital W here, W comes to 0 here, and then since this is G is linear, ultimately it goes to 0. So, this actually vanishes at every point of W. So, this checking is trivial. Now, we have to make sure this. So, how is this defined? G compose of pi, so pi bar. So, according to the definition V plus W, we need to have G compose. So, I have already proved this lies in W star. So, what is the bar of that? The bar of that is nothing but so G compose V, right, because for any F lies in W star we have defined, and therefore, g of pi b, that is g of v plus w, and if you see this is exactly, so g of v plus w, right. So, this is for any v plus w, you see this v this I mean this equals to this, that shows that what we are, that shows what we are supposed to show. Okay. So, that shows this map is surjective. So, this is a surjective linear transformation. So, this map is linear surjective onto, and then what about to 1 1. So, in order to show something is 1 1, what we have to show is if f bar is 0, then if f bar is 0, then f has to be 0, right. That is what we are supposed to show. Fine. What do you need to show if f bar is 0? That means f bar of, if f bar is 0, so f bar of v plus w for any v is, I mean is 0, right. That is what it means. So, how does that define? This is simply f v, right, this is simply f v. So, that means f itself becomes 0. So, then what we have is this map is 1 1 equally. So, therefore, these two spaces are isomorphic, right, and therefore, the dimension will be same. So, dimension of, so as a corollary we conclude that dimension of v equals to dimension of w plus dimension of w naught. Okay. So, these are all the, this is what we have done, and also we would further prove the following, that so of course, this is what I have obtained, and then we would like to prove from here is the following. So, let me go so let me rather do it in this way, that so if this is d, this is d, so dimension of this is n minus d. Okay. So, we do have a basis of w naught, right. So, try to understand. So, what are the basis of w naught? So, since these two spaces are isomorphic, one has a basis of basis f1 up to fn minus d, ordered basis you can say, such that okay. So, rather what we can do is we rather start with so better way of doing this is the following, that let's start with a basis. Let us start with a basis with an ordered basis of v mod w, then consider its dual basis, and and pulling them back, and pulling them back on back to W naught gives us a basis of W naught. Okay. Say f1 up to f n minus d. Okay. So then so these are W naught. So hence what happens to kernel of fi? I run from 1 up to n minus d. So these are all hyperplanes, right, non-zero linear functionals. These are non-zero because they are coming from the basis, they are coming from non-zero elements, non-zero functionals on V mod W. So in particular they will be non-zero functions on V mod W. So that means they will be a non-zero function, yeah. So they will non-zero function. Okay, so yeah. So you have to see here is a non-zero function on V mod W corresponds to a non-zero member in W naught. Okay, a non-zero functional on V which does not, which vanishes identically on every point of S, every point of W. Okay, so it's trivial that W lies inside there, right? Why? Because each Fi is in W naught, so therefore W is contained in the kernel of this, okay, because each Fi vanishes identically on W. Now one needs to prove the other direction. So how to prove the other direction? Because suppose something lies at the kernel of every Fi, okay. So if this is lies at the kernel of every Fi, well, so assume that, so if possible let there exist x not belonging to W such that Fix is 0 for all I from 1 up to n minus d. Okay. So Fix is 0, that means Fi bar, yeah, so Fi bar of x plus W is 0, okay, for all I, and Fi bar. So try to understand what are Fi bars. Fi bars are the coordinate functions or with respect to some ordered basis of V mod W, right. So try to understand, first we started with the ordered basis of V mod W, then take the dual basis, that means the coordinate, as I have seen that the dual elements in dual basis are just the coordinate functions with respect to that ordered basis, then we pull them back. So these are the coordinate functions, and what this shows is that with respect to that ordered basis, for this vector in V mod W all coordinates are 0, okay. So that forces x plus W to be 0, and hence when x plus W is 0, x lies in W. So that is a contradiction. I repeat that the way we have constructed Fi bars are the coordinates of coordinate functions on coordinate functions or coordinate functionals on V mod W with respect to some ordered basis, right. So if that is the case, that means, I mean, for this vector all coordinates are 0 with respect to that ordered basis, and that is possible only if and only if that vector itself is 0, and that shows that x lies in W. Okay. So thus we have proved that any any subspace yeah. So, before that let just a minute, we just a minute, I would like to make sure that everything is correct. So, given W, so it so now it is very perfect. Okay. The further thing is yeah, as this is this the W naught is W. Okay, so in order to talk about a basis of this, what we have to do is we have to make sure that this space is, it does not have the dimension 0, and that is guaranteed by in view of this assumption. Yeah, W is proper. If W is not proper, if W is not proper, then this space would be just a trivial space. So, with there we cannot talk about a basis. Yeah. So, the assumption, our assumption that W is proper is indeed, I mean, has played a very fundamental role in this findings. Okay. So, yeah. So, thus we have achieved what we have promised, that every subspace is the kernel of hyperplanes, and numerous corollaries are they are waiting here. So, several corollaries can be deduced immediately from here. So, yeah, first thing that we observe is corollary. In the very special case, V is Fn and W is a subspace of that proper subspace of Fn. Then we have, so suppose dimension of W is D, then we have n minus d linear functionals on. So, we have n minus d linear functionals on W on Fn such that there the intersection of their null space is W. So, let f1 up to Fn d minus n minus d be those functionals. So, we know that how a typical functional looks like from xn to from Fn to F. So, we will have scalars a on x1 up to ai and xn. Okay. So, therefore, now that means W becomes the set of all. So, in view of this, W becomes the set of all points in Fn such that which satisfies the following, right, a11 a1n n minus d1 a n minus dn okay. So, what does that show? It shows that given any proper subspace, that indeed becomes the solution space of some system of linear equations. So, try to say that earlier we proved given any system of linear equation, its solution space is subspace of Fn. Now, we have proved its converse, that given any subspace of Fn, it becomes the solution space of some system of homogeneous system of linear equations. Okay. So, this is one corollary, and second thing is also corollary 1. If we see, so the second corollary is, what is corollary 2? Corollary 2 is also very easy to see, that here we have found that W is the intersection of n minus d hyperplanes. Okay, n minus d number of hyperplanes. So, the question is whether can we express that as the intersection of less number of hyperplanes. Okay. That is not possible, because if there are functions, let us say g1 up to gm, m is strictly less than n minus d. So, suppose this is the functional the subspace of V naught such that intersection of kernel of gi's m, then first each gi is automatically inside w naught, okay. Each gi is automatically inside w naught, and then we will look at well, so from this what we can immediately see is try to see this in this way, that the kernel of gi's. So, let me denote this by so if this is w, then well, so what I would like to do is I would like to use this as the thing, So, yeah, so hence the subspace, this gi's, if this is exactly this, then what we do is we consider the linear span of. So, I am just giving you a quick argument, and the details are left to you to fill up, because I think I do not have much time. So, g1 up to gm. So, this will be a subspace of w naught, okay. So, in fact, it will be a proper subspace of w naught, the proper subspace of w naught, and so then what is the subspace annihilated by this? So, the subspace annihilated by this is exactly so try to understand this is in general, even in the generality. If let us say a script S contains script S prime, then the subspace generated by this and the subspace generated by that will be, there is a containment relation among them, right, because if the subspace, whatever subspace here is, so the subspace annihilated by this will be smaller than that of here, right, because when you add more number of polynomials, your subspace annihilated by them will be rather smaller, right. When you have more number of polynomials, it will be smaller. So, therefore, what you can see is it challenges the dimension formula, this formula, because the subspace annihilated by this is by my definition W, and so yeah, so well, I think I should leave it here. So, let me leave it as an exercise to you. The main challenge is you have to use this dimension formula that will tell you how to do it. Okay. I have almost given the argument, maybe some further inclusion is to be shown, and that will follow from there. I leave the entire thing to you, the rest to you. So, the thing is what my point is, this is something optimal, all right. So, and the third thing is, so if W1 not equal to W2, then, or put it in this way, W1 perp equal to W1 not equal to W naught. So, one direction is obvious. The proof for the other direction is, suppose assume W1 not equal to W2. So, that means there is a vector lying in W1 which is not in W2. Okay. So, you pass through V mod W2, okay, and so V mod W2 if you take then so x plus W2 is a non-zero vector in V mod W2, right, because x does not lie in x does not lie in W2. So, therefore, this it has one coordinate which is one non-zero coordinate. So, if you fix any basis of W, if you fix any basis of V mod W2, so with respect to that ordered basis it has one non-zero one coordinate which is non-zero, right. So, I mean if the ith coordinate is non-zero, you consider that ith coordinate function f bar and then lift it to and then pull it back to fi, okay, and it is clear that f yes. So, yeah, x belongs to W1. So, therefore, you find what you find is f I yes. So, f I this function. So, f I x is not equal to 0. So, therefore, f I x this does not lie in W1 perp while it lies in W2 W1 naught while it lies in W2 naught. Yeah. So, the proof is you fix an ordered basis here, with respect to that this vector will have exactly at least one coordinate non-zero. So, let us consider the ith coordinate is non-zero. So, you take the ith coordinate function with respect to the ordered basis. So, that function corresponds to function f I in W2 naught, okay. But that function in W2 naught this cannot have, it is 0 from this definition. Therefore, f I 2, so f I lies in W2 naught, but not W1 naught. All right. So, that shows that a subspace is uniquely determined by its annihilator, okay. Fine. And as I see that this one I left somewhat incomplete, I feel that this is the complete argument. If you think there is some problem, and the way of proving this is precisely the dimension formula. If you see some it's there is some incompleteness, then I would leave that to you to fill it up on your own, or maybe if time permits I can get back to this. Okay, let us now move on. Fine. Now, let us for the rest of this we will now talk about bidual or double dual. So, what is that? Given a vector space V, we talk about let us assume finite dimensional, then one talks about V star that has dimension same as V, and then V star is also a vector space. So, we can further talk about its dual. So, this is called a double dual of V. Okay, this is the double dual of V. Okay. So, we have a very natural map from V to the double dual of V. What is that? So, starting with any V, so what we can do is, so what is V double dual? V double dual is a space of all set of space of all linear functionals on V dual. So, we define a map, let us call it evaluation at V, and this is exactly as follows, that what is evaluation of V? Evaluation V is a map from V to, is a function of V to F. How is that defined? EV of F is f of V for every F in dual. Okay. So, V is being mapped to evaluation V, and that is very easy to see that this map is linear, because E V1 plus V2 of F for every F is F V1 plus F V2, F V1 is E V1 F and the other one is F E V2 F. So, this map is linear. Okay. Next, so what are is that 1 1? So, if EV is 0, E v 0 means for every v, f of v is 0 for every f, okay. And if you fix an ordered basis in v as usual, then if you have an ordered basis in v, then consider the coordinate functions with respect to the ordered basis. So, if you take f to be the coordinate functions, then this shows that all the coordinates with respect to the ordered basis, all the coordinates of v will be 0, therefore, the vector v is itself 0. So, therefore, this is one, and that is very interesting now, because we know that for any v, dimension of v equals to, for any finite dimensional v, dimension v equals to dimension v star, and dimension v star is same as dimension v double star, okay. So, therefore, what you get is dimension v equal to dimension v double star. So, these are the same dimensional vector space, you have a 1 linear map, therefore, this is an isomorphism. I mean, try to see what is happening. So, dimension v equals to dimension v star for any finite dimensional vector space v, okay, because corresponding to every ordered basis we have a dual basis. Then dimension v star is also a finite dimensional vector space, so its dimension is same as dimension v double star. Therefore, these have the same dimension, and then this map is linear and injective, so therefore, it will be isomorphism. So, I would like to make 2 remarks here. This is a very important thing. Try to understand the, when we establish that v is isomorphic to v star, how did we do that? We fix an ordered basis, then we, so we saw this is isomorphic to this, okay. Then corresponding to this ordered basis, corresponding to the ordered basis, we saw, we construct a dual basis for that. So, therefore, we see that that is also isomorphic to Fn because same dimension, hence by composing we get this isomorphism, right. So, try to see that the isomorphism from v to v star, that indeed depends upon the choice of the ordered basis b, otherwise you do not have, and I mean you do not have in general an isomorphism which does not depend on the choice of v and choice of our ordered basis. But surprisingly, when you compare v and v double star, there you indeed has an isomorphism which does not depend upon any, does not involve any choice of an ordered basis. So, I mean the such maps which do not depend upon any choice of ordered basis, we call them canonical. So, from v to v double star we have a canonical isomorphism, but we do not have a canonical isomorphism from v to v star, that is the point, okay. So, this isomorphism is independent of any order choice of the ordered basis. Now, what we can do is, in view of that, we have some immediate conclusions. So, the first conclusion is, try to understand this map. So, this isomorphism shows that every corresponding to, if you take any linear functional, it shows any linear functional on v star is basically some evaluation by some vector in v, that is what it shows, okay. That is what it shows. So, then what should be the very natural corollary. So, corollary to this is as follows, that let say f1 up to fn be a basis. So, let the dimension be a basis of basis of v star, okay. So, we start with a basis and then consider its dual basis. So, the dual basis of the, let us denote them by f1 the star is the dual basis. So, it is now a basis of v double star. So, it is a dual basis with respect to F1 Fin. Okay, so dual basis, yeah. Now, what's the immediate? So, F1 star, F2 star, Fn star in a V double star. So, that means there exists alpha 1 up to alpha n in V such that F1 star is nothing but if I is nothing but E alpha I. Okay, if I is nothing but E alpha I. Now the things are very obvious that we claim that alpha 1 alpha 2 is a basis of V. Why so? That is very easy. So, if you take any vector V, go to EV, you know that for EV you have, let us say, I should have written V1 up to Vn. So, Vi V1 up to Vn. So, you know that we have summation alpha I EVI V1 up to n, and therefore, yeah. So, okay, so it's enough to show that it's independent because V has dimension n. So, if we show that this is a linearly dependent, then it will be proved as a basis, and how to show is linearly dependent. So, yeah, if alpha 1, that is fine. Now that is more clear. So, if alpha 1 V1 plus alpha n Vn equals to 0, then we using the linearity here, we get that summation E alpha this is 0, okay, because this is the linearity, and yeah. So, yeah, E of alpha. So, this is just by linearity E of, yeah, that is fine, that is fine. So, since this is a basis of E of Vi, and what is E of Vi? E of Vi is Fi star, and Fi star is a basis of this is a basis in this. So, that means each alpha will be 0. Okay. So, this is a basis of V, and now the interesting part here is the second claim. So, throughout we assume that these are not just bases, in fact, with this natural ordering. So, they are all actually ordered bases is the basis of V star dual to how does that is proved? That is very easy, that what is Fi of Vj. So, Fi Vj is according to my definition E Vj of Fi, okay, and E Vj is according to my definition Fj star Fi, which is del Ij. So, we are we show that in. So, what did we prove? So, earlier we proved that corresponding to any basis in V, we get a dual basis of V star, okay. But the question was open at that time, that whether every basis is a dual basis of some basis, every basis of V star is the dual basis of some basis in V or not. Again, by basis here we, I mean, though we are saying basis, we are tacitly assuming the bases are ordered. So, once we assume that, then then we have just proved that indeed this is the case, that every basis of V star is the dual basis of something, a dual basis of a basis in of V. All right. So, yeah. So, we finish this lecture with some remarks. So, if you remember the notion of annihilator here. So, we proved that a subspace is determined uniquely by its annihilators, right. So, that means given a we proved that if the subspaces are different, then annihilator should be different. So, therefore, we if I am given the annihilator of a subspace, from that how can I get back the subspace. So, suppose for a subspace W, if I am given W naught, then how can I get back W out of that. Okay. So, that is very easy to see in view of this V dual. So, one thing you should observe that once we identify V with V dual by this, so every member is V dual is some evaluation at V. So, therefore, naturally we have a very natural canonical identification of V to V dual. So, therefore, V dual is to be regarded as V, and also the every basis is that corresponding to a basis here you have a dual basis there, and for any basis here you have a basis on V which is the dual of that. So, therefore, it is natural to regard that V and V star are dual of each other, right. V and V star are naturally, they are in natural duality with each other. V and V star are in natural duality with each other. With natural duality in each other. So, therefore, from V you come to V star, and then further when you will get back to V, okay, and the getting back to V is by means of this identification. So, now we come to the problem that suppose W for a W star is given. So, W star is a subspace of V star, then we would so you would like to find out V. So, find out W. So, what is W? So, in W star, if you remember, in W star, what was W star? So, let me first look. So, from W to, from a subspace W to, we can go to W naught which is inside V naught, and then it makes sense to get inside V double dual which is same as V by that identification. So, what is the annihilator, double annihilator of W? So, in view of this identification, is it not? So, well, since I do not have much time, I should finish. So, what is W double naught? So, we are looking at all linear functionals on V star which vanish at identically on W naught, right, which vanish identical on W naught. Okay. So, and the linear functional on V star are precisely of these forms. So, therefore, we are arriving at the following set of all vectors such that f v equals to 0 for all f belonging to W naught. So, in view of that identification, because if we say that we will all the members in W in V double dual are of this form. Okay. So, all linear functionals here which vanish at all point of W naught is precisely this, and what is this? So, I leave that as an exercise to you because I do not have time. So, W double naught in view of this identification is equal to W itself, okay, in view. So, I would like to leave this as an exercise to you, and with that I will finish. Yeah, thank you.